Hello dear students, welcome you all. In this lecture, I am going to discuss about the next thermoelectric effect, that is Thomson effect, right? Thomson effect, right? This is the next thermoelectric effect that we are going to discuss in this article. We have already, studied Seebeck effect, Peltier effect, and now we are discussing Thomson effect. This is named after physicist William Thomson, right? William Thomson, studied it in detail and verified in 1851. Although this effect was predicted by Lord Kelvin, right? But William Thomson observed it experimentally and verified it. That's why we call it as a Thomson effect, right? It is the next application of thermodynamics to the thermoelectric effects, right? Now, what is Thomson effect? When we allow the passage of electric current through a unequally heated conductor, right? Then heat is either absorbed or evolved along the length of the conductor, right? Depending upon the direction of the flow of current, right? This effect is called Thomson effect. Now, here we are using only one metal, one piece of metal, instead of using a thermocouple. So we can say that this effect is shown by individual metals, right? Here we are passing electric current through a metal. It can be copper, iron, or something else, which is unequally heated. It means the different parts of that conductor were at different temperature. So when we allow the flow of current through that conductor, then there is always either absorption or evolving of heat along the length of a conductor, and this depend upon the direction of the flow of electric current. We will understand it more clearly. Let's consider copper strip, right? We have a copper strip here. This is copper strip. This is I'm going to heat this copper strip by placing a burner here, right? Right. So this is burner, gas burner, that is heating this copper strip at this middle point, right? This is the midpoint of this copper strip. This is the uh, end A, and this is end V of this copper strip. I'm hitting it from here, right? Uh, then this is copper. Define it. This copper. Right? Let's pass electric current in this direction from A to V along this copper strip. Now we can see here that obviously the temperature is higher before the passage of current. It is at high temperature, this part, as compared to this part, right? This is at low temperature, this is again at low temperature as compared to this point, right? Now you can see here that at this point, clear, from here to here, right, in this region, the electric current is going from this low temperature region to high temperature region, right? Whereas here the electric current is going from a high temperature region to low temperature region. I can say low to high and high to low. We know very well that when we heat a conductor, the concentration of the free electron changes, because the concentration of the free electron depends upon the temperature, right? It means the concentration of free electron, density of electron is different at this point at this point. Clear? These two points have a different concentration of electrons, free electrons here also, right? It means here, between these 2 points, this one and this one, there will be a obviously potential difference, right? And here also there will be a potential difference, right? So, current is going from, when one end to another end, it is passing through the different gaps of the potential. I can say, let's erase it from here. I can make it more clear. I made here a potential, uh, you know, walls. Now I can say here it is, the potential is different here. Here it is different. Here it is different, right? As I told you that the density of the electron is different. Here it is temperature is low. Here temperature is high. When the temperature is high, the density of the electrons will be, low at this point. Whereas the density of the electron will be high at this point, right? So, as I told you that here I can say at this point, electron density is high, sorry, low. When the temperature is high, low, right? Whereas at this point, or this end, it is high. Again at this end, it is high, right? So when electric current is going in this direction, it means the electrons inside the strip are trying to flow in this direction, because the electric current and the direction of electrons are opposite to each other. It means, sorry, when current is going in this direction, the electrons are flowing in this direction. It means when the electron goes from this side to this side, they are going at this point from high electron density to the low electron density. So obviously they are flowing easily, right? It means heat will be evolved. Heat will be evolved, because there is a ease for electron, easiness for the electron in going from high electron density to low electron density. This is the natural tendency. What here, when they are going here to here, what is the result? They are now going from low electron density to high electron density. So they are going exactly opposite to their natural tendency. It means work has to be done in order to overcome this, right? Potential arising due to these two electron densities. So it means when the electrons goes from low electron density to high electron density, work is done. It means heat should be absorbed, right? So I can say, I can highlight it separately. Heat absorbed, and here at this point, along this side of the conductor, heat will be evolved. So you can understand it in this way. I can understand it in another way in terms of the potential, right? Here it is low potential, right? Because here electron density is high. Here it is high potential because electron density is low. This is is the value of the electric potential according to the concentration of free electrons. Here again the potential is low, and here it is high. So here we can say the electrons are going from low potential to high potential. So this is their natural tendency, right? So they will release energy in the form of heat. So heat will come out along this side of the conductor, whereas in this side of the this conductor, they are going from higher potential to lower potential, right? Now this is against their natural tendency, right? So obviously it means heat will be absorbed, right? So this is the explanation of the evolution and absorption of heat along the length of unequally heated conductor. So here in this case of copper, we can say that here it is heat absorbed and here heat evolved. It means the heat is getting transferred along the direction of flow of current. Heat is absorbed here and then it is evolved here. So heat energy is getting transferred along the direction of the flow of current. So we call this type of effect is a positive Thomson effect. So when the heat is transferred along the direction of the flow of electric current, then this is called positive Thomson effect, right? The other metals that show positive Thomson effect are cadmium, zinc, silver, and antimony. They also show positive Thomson effect, right? And this effect is reversible. If I reverse the direction of the flow of current, obviously the heat absorbed and heat evolved will get exchanged. If I try to flow current in this direction, then heat will be absorbed here and heat will be evolved here. So remember it that Thomson effect is reversible, right? Now I am taking the another case of different metal, that is iron. So for it, consider a strip of iron. Again, I am going to heat it at the middle by taking a burner. Right. So this is the case of, this is end A and this is end B. Now this is the case of iron, Fe. Clear? This strip is of iron. So here we are heating it at this point. By the application of one, right? Now in this case, when I allow the passage of current in this direction, right? In this case, the things will be opposite, right? In this case, heat will be evolved here in this part of the heat will be evolved, and here heat will be absorbed, right? It means it is exactly opposite. This is center, let O point. It is exactly opposite to this. It means in this case the situation is different, right? It means in this case, if I draw the potential wall, then it will be right. So you can see here that in this case it is high potential, it is low potential, it is again high potential. It means when the electric current is flowing in this way and electrons are flowing in this way, here they are going from high potential to low potential. It is against their natural tendency. So heat will be absorbed, they require additional energy, right? But here, when they are going here, they are going from low potential to higher potential. So this is in accordance with their natural tendency to flow from low potential to high potential. They always want to go from low potential to high potential. So here they have extra energy, so they will release their energy in the form of heat. So this heat energy will be evolved along the side, this side of the conductor, whereas along this side heat will be absorbed. So in this particular case of iron, we can see that the heat energy is transferred in a direction opposite to the direction of the flow of electric current, right? Current is going in this way, whereas heat is going in this way. It is absorbed here and it is evolved here, right? Whereas in this case it was absorbed here and it was evolved here. So you can see the difference. So we call this type of effect as negative Thomson effect, right? There are other metals also that show negative Thomson effect, cobalt, nickel, right, and mercury, right? They also show negative Thomson effect. This type of effect is called negative. There is one metal, that is lead, right, that show this effect as 0, right? Means there is no absorption or evolution of heat when the current is allowed to flow through the lead, when different parts of lead are at a different temperature. It means if I take the case of lead instead of iron or copper, there will be no transfer of heat. So Thomson effect for lead is 0. This is called Thomson effect, 0 Thomson effect, right? 0 Thomson effect. Means Thomson effect is 0. It doesn't show heating or cooling, right? So this is about the Thomson effect, positive Thomson effect, and negative Thomson effect, and 0 Thomson effect. Now I am coming to the Thomson coefficient. So it is observed that the amount of heat evolved or absorbed is directly proportional to the flow of current. In the metal, it is directly proportional to the time for which the current is flowing. It is also directly proportional to the temperature difference between the two ends, from here to here or from here to here in the conductor. So I can write Q directly proportional to I T dt, right? If I remove this sign, Q is equal to sigma I T dt. So I can write sigma is equal to Q upon I T and dt. So this constant of proportionality is called Thomson coefficient. So if you take I is equal to 1, T is equal to 1 second, I is equal to 1 ampere, dt is equal to 1 Kelvin, then what is sigma? Sigma is equal to Q, right? So Thomson coefficient is defined as the amount of heat energy evolved or absorbed when unit current flow through a conductor for unit time whose whose two ends are maintained as a temperature difference of 1 Kelvin, right? So this is a definition of Thomson coefficient. If I look at the units, then obviously I can write units from here. It is joule, right, per ampere, per second, and per Kelvin, right? This is the units of this. So this is all about the this Thomson effect. One thing that I also told you in this lecture, that this effect is also reversible, right? It means if I reverse the direction of the flow of current, the direction of the transfer of the heat will be reversed, right? So this is all about the Thomson effect. This was the another type of a thermoelectric effect in addition to Seebeck effect and Peltier effect, right? So thank you very much.